Welcome back to our lecture series in engineering mechanics, for which we already started talking about rigid bodies in equilibrium. Specifically, what we have covered so far were simply supported beams, and if you noticed, those simply supported beams only carried concentrated forces or point forces. Today, our goal is to expand that to the next structural type and to include additional types of forces. So today I want to talk more about cantilever beams that then carry what's called distributed forces. So we of course want to introduce this one by one, and therefore my first goal is to actually introduce to you what distributed forces are. Sometimes engineers use these for self-weight description of structures, but they can be used for different purposes too, and you will understand how that works today. Then we need to refresh our understanding of the fixed supports so that we can use them to talk about cantilever beams. And that will take us into our ultimate goal, or one of our ultimate goals today, which is to actually use those two first goals and calculate or determine the support reactions for cantilever beams that carry evenly distributed forces. As soon as we have that knowledge in place, we can actually further extend our knowledge and talk about non-evenly distributed forces. That's just one step up from what we will talk throughout most parts of the lecture. And because we're talking about cantilever beams, we will also apply these non-evenly distributed forces to cantilever beams and calculate their support reactions using those types of forces. So let's get started and first talk about self-weight, or what's properly called evenly distributed forces. Self-weight is just one implication of evenly distributed forces, but they can also be used differently. So what we usually do in the classroom to kick off this type of understanding is, let's take a look at the table in front of us, and I would usually ask you, how long do you think the table in front of you is? And you can play along with this. You can find a table in your home and just pick any random table. It's good if it's a rectangular shape. It makes the concept easier to understand or easier to follow. But take any table and estimate the lengths and just add the lengths here to the system. The one that we use in the classroom, although we sometimes disagree in the beginning, but once we find a common sense in the classroom, we usually say that it's a 2-meter long table. So that table has a specific length, and what I then ask my students next is to go ahead and actually lift the table to tell me how heavy the table is. And I invite you to do that too. And what you probably will do, just like my students in the classroom, is put one hand right here, and then the other hand goes somewhere here on the other side so that you can lift it in one upwards motion. Now, I have no idea how heavy the table in front of you is, and you would be surprised how students can disagree on this even if they lift the table. So we usually have a discussion and then come to a common agreement, and that is usually that it's 30 kilograms, let's say, or at least that's a good number we can use for the example, which then gives us a weight of 300 Newton. But then the fun part starts. I ask the students to not use two hands, but only use one hand to lift that. So we usually find the second strongest person in the classroom and have them lift the table and only use one hand. And I invite you to go ahead at home right now and take the table in front of you and lift it with only one hand. And although I'm clearly not seeing you right now, I can obviously predict where you lift the table and how you do that with one hand. You place the one hand under the table, probably right here. And I guess you actually have 4 fingers and 1 thumb. So let's do that. Now, why did you do that is the big question. You intuitively knew that the table is actually a rectangle and the force is evenly distributed. You knew that the force is acting in the center of gravity. You may not know it as the center of gravity, but if you draw the diagonal through a rectangle, you will know that the force is actually acting right there. And what you have done, you have applied engineering mechanics concepts, because everything here to the right of the force balances everything to the left of this force, right? So let's keep in mind that this force is 30 or 300 Newton. So we have 300 Newton acting there. And then for the next part that I asked the students in the classroom, we of course have to do this virtually and not in reality. I asked them to, what happens if you actually bring in a saw and you cut the table in half? So what you would do is you would cut the table in half along this line, and then you would have to lift each half. First of all, how heavy would each half be? You are correct. Each half would have a mass of 15 kilogram now, because you cut it in half, and therefore you have 150 Newton. And if you were to lift that half, you would clearly do that along another diagonal, or again in the center of mass, which, because it's a rectangle, would be right at those diagonal intersection points once again. And we can play this game over and over and over again. So what I asked the student next is, hey, what happens if I cut it once again along that diagonal? So I now cut it in half one more time so that I actually have quarters now. And then of course, what you will find is that you have 7.5 kilograms, which is equal to 75 Newton. Now you can continue this over and over and over again, but you have to look at this in context of the actual lengths. So for example, for the first part here, for the 300 Newton, we had a length of 2 meters per piece. And then we cut it into two pieces and we had 150 Newtons for 1 meter piece. And then last but not least, we had 0.5 meter pieces that then had 75 Newtons. Of course, an engineer would never describe a tabletop by saying that, hey, a 2 meter tabletop has 300 Newton weight. An engineer would always unify this, and you can see that these can all be unified to the very same number, and is actually given here. It is actually 150 Newton per meter. So if you have a 2 meter tabletop, then you have 300 Newton. If you have a 4 meter long tabletop, then you have 600 Newtons, and so on. And so the best way to describe that actually is by 150 Newtons per meter. So this is how engineers describe self-weight. They would say, hey, 150 Newton per meter. And let's be clear about what that meter is. So let's go back to our table here and let's actually add some dimensions to that. So for example, I can use the x direction in line with the longitudinal axis of the table. And I can also have a y direction, because we're dealing with 2D systems here only, so y. And then I also have a z direction, but we will make the z direction disappear in just a second. So here we have a z direction. And of course, the engineer would say, hey, this is floating free in space, so we need table legs. So let's just pretend that we have a leg here on the left side and on the right side, just to make our life easy. And maybe they even have some depth to it. So to make our life further easy, the leg is actually a wall on the side, just so that we don't get confused about that. And so it would probably look something like this. And that would be our table leg, let's say, which of course is a table wall. And that can now be idealized as a 2D system, and that is what we deal with in this class mostly, so that's why we're talking about it that way. So let me go ahead and idealize this in a fashion that you already have seen. So it is a rigid body, and because it is a rigid body, it deserves this dashed line that we haven't explained much in the last lecture, but we will talk more about that today. So of course I need to idealize my table legs as well. And now let's talk about that reference fiber, as we will call it later, because the reference fiber, the dashed line, is actually telling us that the x-axis is moving horizontally, whereas the y-axis is always on the opposite side to the reference axis, positive. So this is positive y and this is positive x. And you can imagine that if the reference fiber would be on the other side, then my x-axis actually points to the left side and my y-axis, positive, goes down. We will learn more about this later, but I just want to give you a reference to why we draw these dashed lines. So one, we needed to identify a rigid body and not a cable, right? So it identifies a rigid body, but it also identifies the positive x-axis and the positive y-axis. But what we want to talk about, of course, is this 150 newtons per meter, because we want to talk about evenly distributed forces. So the way engineers would draw this on top of the structure is something like this. Some people actually use a waved line instead of a straight line. I prefer to use a straight line, as you see here, but engineers would definitely use these arrows, and then we would call that W, and sometimes W1, 2, 3, whatever you want to call it, but W is equal to 150 Newton per meter. But I want you to now understand what that per meter means. The per meter means in the x direction, right? So we're talking about 150 newtons per meter in this direction. So this is what this per meter means. Of course, you also have a per meter in this direction, which we kind of ignored. We kind of compressed the depths here, the z direction, and we're just saying that this entire tabletop is carrying 150 newtons per meter in the x direction. And why do we say 150 newtons per meter? Because we can just multiply that by 0.5, and then we know how heavy half a meter would be. We can multiply it by 2. We would know how heavy 2 meters would be, and so on and so forth. So engineers use this as a common way to express how heavy something is if it's repetitive, right? So if it has the same density and it moves with the same force along the x-axis. But besides the unit here and the distribution of the force, and you can see that it's evenly distributed by this straight line. Again, some people use actually a wavy line. I don't like to do that because it means that it's not evenly distributed to me, but some people prefer a wavy line, so you might see that in some textbooks. However, because it's an evenly distributed force, remember that by the very first experiment that you did by lifting the table with one hand, you applied this here in the center. And so you know where this force is actually acting on this structure. So engineers can use that, and they can use a method that's called lumping the force, right? So let's say I have my structure here, and I can now lump the distributed force into one location. Before I do that, I of course have to bring my support reactions down here, and then I can go ahead and actually lump the force into the single location where you originally placed your hand. So it's acting in this place here at 1 meter, at x equal to 1 meter, and we call that F. I often call that F resultant, but really what that is the lumped force. Lumped force. And that can be calculated by using the two units of the 150 newtons per meter along the x-axis times the length of the x-axis. So I would calculate this as 150 Newton per meter along x, and by the way, that x will later not be shown in those calculations, multiplied by 2 meters. And 2 meters is really where the force is acting, or about which direction the force is acting. So acting over that distance. So sometimes you see beams that carry only like a portion of this. In fact, you will see this later today, not the entire beam. So of course you can only multiply it by the length it's acting over. And what you will find, of course, here in this case is that we end up with 300 Newton. And notice the unit, right? So here we have a force of Newton, whereas here we have Newton per meter, because we're trying to convert this into a force at a specific location. And let me give you one quick warning before you get too used to this. This I only explain right now to get the point across of how this works. Please do not form a habit of drawing this in your free body diagrams. If you do that, you run risk that later on when we calculate internal forces, that you don't understand the meaning of the distributed forces or the impact that they have on internal forces. And this may be puzzling to you right now, so just take it as I say it for now. Do not draw this all the time. It forces a wrong interpretation of the lumped force into you. So this is only to describe the concept here right now. Please do not use this picture in future assignments, because there will be a point later in the class where you really have to think of these distributed forces as distributed forces and not as a lumped force. But while we calculate support reactions, and that is our topic that we're still working with, while we're doing that, we can think of them as lumped forces. But I think that gets the point across, right? So you calculate the intensity per meter times the distance, and then you need to know where it's located. And notice that this here is effectively a rectangle, right? And how do you calculate the lumped force of a rectangle? You take the base, 2 meters, times the height, which is 150. And then you place the lumped force in the centroid location of this rectangle. Right? It's kind of similar to what you did here. Here, of course, it's a 3D picture, so please do not confuse this. But the lumped force here is acting within the center of this rectangle. And I say it again, you calculate the rectangle as base times height, and that will be a concept that will be very important for you later on. So please keep that in mind. But for now, what we're left to do is, how do we calculate these support reactions? And in this case, it's super simple because we used a symmetric system, but let's go ahead and explain that in terms of the distributed forces. So if I were to calculate RAY and RBY, then I would say that because it's a symmetric system, I actually have half of the lumped force, right, each. And you already understand this from when we took the table apart or when we sawed it apart. So we can say that RAY is equal to 1/2 F resultant, right? And so that in our case would be 300 divided by 2. But here comes how engineers really would write this, by using the evenly distributed force. So engineers would say it is 1/2 150 Newton per meter multiplied by 2 meters. And again, that's not very different. It's kind of like already built in, but that's how you would do it, right? And so the way that you can actually calculate this by taking the sum of the moments about a point, right? So let's do that here on the side. So let's find, for example, RAY is the sum of the moments about point B being equal to 0, counterclockwise positive, and then 0 is equal to minus RAY multiplied by 2 meters, because that's the distance between the point of reference and RAY, and then plus 150 Newton per meter multiplied by 2 meters. And this is often where students stop, so let's take a break here and think about this. What do we have here? Here we have Newton times meter, and here we have Newton per meter times meter, so this would be Newton. And you cannot physically combine Newton in one equation with Newton meter. So we need to multiply this by its lever arm too. And you guessed it right, the lever arm here for the lumped force to support B, because remember, this is where we take the sum of the moments about. So we take it about this point. So I need to worry about this force, the lumped force that I just lumped here, and multiply it by the lever arm, which is 1 meter. So let's do that, 1 meter. And let's say that this here is F resultant, and this is the lever arm. And just because it's the very first time we're doing that, let's make sure that we understand that the distance here is what we're talking about. So we're talking about 1 meter here, because that is where the force is lumped. And this, of course, you can use for any type of distributed force. And I encourage you to really make sure that you follow this concept, because that is something you will use over and over again in your future assignments. But that concludes evenly distributed forces, which, as you have seen, we can use to represent self-weight. Now, you can, of course, sometimes superimpose self-weight. So, for example, if I want to use the table example, let's say I have the table here with its self-weight on it, and let's say the self-weight is this, then you can practically think of this. What happens if I actually add a book to it? So let's say I place a book here that also has an evenly distributed force. So that then can look like this. And of course, you then have to deal with the individual lever arms. So let me give you those lumped forces as well. So the first one, the red one, would probably have a distributed, not probably, it would definitely have a lumped force where we indicated it before. So this here would be F, what I usually call resultant 1. But we also have another one, which then is F resultant 2. And of course, they have their individual distances, as you can see in this image, to the support reactions. So I would, for example, need 2 lever arms, depending on which side I'm taking the sum of the moments about. So let's call this here A and this here B, and this then would be 2 and 2. Whereas for my first force, I have A1 and B1, right? So you get the point that these distributed forces are not just self-weight of a structure, they also can represent some self-weight of something else that sits on the structure, or other types of forces that you will learn about later. And of course, each one of them has to be lumped up by using base times height. So, sorry, base times height. And you can do the same thing here, base times height, whatever that value would be. And then you have to understand, where do those forces act? How far are they away from your point of reference? And that concludes our self-weight or evenly distributed forces. And we are now ready to take it to the next step and move away from simply supported beams and actually talk about fixed supports, so that we can ultimately solve cantilever problems. Let's go ahead and do that. I am certain everybody remembers the fixed support when we talked about support reaction and when we defined the 3 different support types. So right now we only have to refresh them. Let's talk about fixed supports, and they can be represented in different ways. One of the most common one is probably with the line through the wall, as I do it here, but sometimes you also see them, for example, in a different way. So let me draw that. So sometimes you also see them as such. And it doesn't really matter how you do it, as long as you understand what the purpose of this symbol is. And the most important one that we remember is that we needed 3 conditions to be true for our systems so that they can support forces. And what were those conditions? We said that the sum of the forces in the x direction must be equal to 0. The sum of the forces in the y direction must be equal to 0. But also the sum of the moments about any point must be equal to 0. Now, what that means in terms of a cantilever beam, and you can think of this as a balcony, right? The balcony that you probably have in your apartment complex or wherever you currently are. I'm sure you can find a balcony somewhere around you. You can see that there's only one support and not, as we had before, 2 types of support at A and B. So here we only have a support at A. And that support now needs to prevent these 3 things all in one. And that's why the free body diagram for this type of support looks slightly different. Keep in mind that the picture that you see above here is not a free body diagram. A free body diagram has the forces in it. And so the forces that I need is I need something that prevents vertical motion. I need something that prevents horizontal motion. And we usually call those, let's say, RAY and RAX. But we also need this third condition to be true, which before we always solved by putting another support here. That was a simply supported beam. Now we cannot do that. We have a cantilever beam. So that means what this support has to offer is a rotational resistance, right? So we need something here, which we usually call M at A about the Z-axis. And so you can see that if you provide this, the system does not fall down, it does not move left and right, and it does not rotate. And that is important for our static systems so that they actually remain stable. And all these three conditions have to be met. Without that, it does not work. And why am I saying this so repetitively? Because often I see students look at these structures and then they find RAX, they find RAY, but they don't find the moment. And that's actually the most important one. And probably it's also an easy one to find because you do not have to deal with unknowns anywhere else than at this location. So the only unknowns in your system are usually at this one support, and that makes your life very easy and very fun. So let's look at that, how that is implemented. For example, if I were to place a self weight on there, so let's pretend that this here has a self weight and I use just, let's say, 10 newtons, so 10 newton per meter. And let's make our life easy and let's make it, what, 4 meters long. So 4 meters long. Then what I would do is I would calculate, let's say, my RAX first, and I would do that by the sum of the forces in the x direction being equal to 0. And of course you find that 0 is equal to RAX. And I don't have to worry about that anymore, but it is still a result because there could be a horizontal force on there. Now RAY is very simple to calculate because you only will end up with one unknown, as I said. So the sum of the forces in the y direction is equal to 0, upwards positive. By the way, here I should indicate that too. And 0 is equal to, and I assumed this to go upwards, which makes sense, of course. So plus RAY minus 10 Newton per meter multiplied by 4 meters. And be careful now, because remember what I said earlier, sometimes students confuse things when it comes to these units. So here we have 10 newtons per meter and multiply it by 4 meter, and that goes hand in hand with what we have here. So now we only have a force here, and Newton per meter multiplied by meter is a force. So therefore this equation is already complete, and we would find that RAY is actually equal to, careful, plus 40 Newton. And that is what we want. We want a force, right? So this is an answer. And now we are left with the last unknown. And the last unknown would be MA. So MA, I now find that, and this is the first time you see this, I find this by taking the sum of the moments about any point, right? Remember, I can always take the sum of the moments about any point. If the system is not rotating, if this system does not rotate, then I can take the sum of the moments about this point, this point, this point, this point, this point. It doesn't really matter, but the smartest point to take is probably this point, because then I don't have to include RAY into my equation. And actually also not RAX. If I were to take about, let's say, this point, then I would have to include this and this. And I want to avoid that, so I take the sum of the moments about point A. So let's go ahead and do that and say that is equal to 0, counterclockwise positive, and 0 is equal to, and I start with my unknown as always, MAZ. I assumed it here to turn counterclockwise. That makes it positive according to my definition. So plus MAZ. And now I need to find the lumped force there of this system. So 10 Newton times 4 meters. And then it has a lever arm of 2 meters, which then rotates clockwise. Therefore, that is negative. So let's say minus 10 Newton per meter multiplied by 4 meters. And remember where that is acting. It acts exactly in the center. So multiplied by 2 meters. And just because we're still learning this, this is the F resultant, or the lumped force, and this is the lever arm. And this, by the way, is the rotational sense. So please keep that in mind. And I want you to pay close attention to this again. You don't have to, but it is so much better to take the sum of the moments about this point where MA is acting when you find the support reactions. If you do that, you will be very thankful later on when we move into internal forces for reasons that I cannot explain right now, but you will understand them when we get to internal forces. However, if you do that, it will be very helpful for you, and you should memorize this. Always take the sum of the moments about that point where the cantilever is supported, so that you can actually use this equation where RAY and RAX does not influence this equation. Nevertheless, we can now calculate actually that our MA, so MA is actually equal to what? 40 times 2, and that is actually positive. So plus 80 Newton meters. This is also important to understand, right? So it's a moment that we're calculating. Therefore, it needs to be in the units of a moment. And we have that because this cancels out this, but the other distance remains, the other m remains. And you understand that we need to end up with a force times lever arm. Also important is this positive here. What does the positive tell me? Similar to what we talked about in the last lecture, this positive does not necessarily tell me that it's clockwise or counterclockwise. It just tells me that I assumed this direction correctly. And this can be confusing sometimes because so often the plus here coincides with this being counterclockwise. But that is only true because I defined it as such. Really, you need to read these pluses for your support reactions as, hey, either I was right, plus, or I was wrong, then it would be negative, right? So what this plus means is you interpreted the direction correctly. For example, if I had assumed MAZ to go in this direction, what would have happened? Then I would have ended up with a minus MAZ in this equation here. And then I would have found that I end up with a negative here, right? So then this would be negative 80. And I encourage you to really think about this if you understand this, how this equation would affect this to be negative. And when that is negative, then I would say, hey, it's not turning clockwise. It actually means I assumed this arrowhead incorrectly, therefore I need to turn it around. So please understand that this tells you being right or wrong. It does not tell you clockwise or counterclockwise. It's a common misunderstanding because we have defined it here as such, and students have not enough experience in the beginning to understand the difference between the clockwise, counterclockwise versus correct assumption and incorrect assumption. But take my word for it, this plus only tells you that you assumed correct. For this part here, you would have found that you assumed incorrectly, and therefore you would have to reverse your logic. But to sum up the fixed support refresher here, please understand that we have 3 support reactions that are symbolized by this little symbol with the 3 lines that are diagonal. And also notice that there's no circle here, so it's kind of clamped in. In fact, the way you can represent or think of this is take a pencil in your hand and don't let it fall down. Take it in one hand and you pretty much perform the action that the wall usually performs on the balcony, right? So this clamps this beam, and because it clamps, you don't just have the vertical and the horizontal force, you also have the rotational force. And that guarantees that all these three equations can be satisfied by just one support reaction. And that gets us ready for our examples, and we can now go ahead and solve cantilever problems with distributed forces on them. Welcome to your first example problem for cantilever beams with distributed forces on them. And here we have a very straightforward example. We almost solved it already in the lecture, but let's just complete this here as well, because it helps us to further understand it. And notice that it says determine all support reaction for the cantilever beam with the different forces on them. We have a concentrated force of 10 kilonewton here and 3 kilonewton per meter over a length of 6 meters. And so the first thing that we have to do is draw our free body diagram. So I will pull out my ruler here and draw this rigid body, and rigid body means that it has a dashed line underneath it, which then indicates the positive x and positive y axis. And what often students do is something incorrect that I will erase in a second, but they draw the free body diagram as such. That is not correct because it is not a force indication. You have to bring in the forces, and the forces that you have acting here are actually the vertical force, the horizontal force, and the rotation. So the forces would look something like that. And I just make an assumption here. I assume RAY to go in this direction, RAX in this direction, and MA about the z-axis to rotate clockwise. Now the forces that act on the structure I also have to include. So I have this distributed force, and then I have the concentrated force as well. So I have 10 kilonewton here, note the units, and I have 3 kilonewton per meter here. And now I can go ahead and solve for my unknowns, which are all in one location, and that will make my job fairly easy. Let's go ahead and do that. So for example, I usually start with RAX, which is calculated by the sum of the forces in the x direction being equal to 0, positive to the right, and 0 is equal to plus RAX. And that is already done because there's nothing else in the horizontal direction. Now for RAY, I take the sum of the forces in the y direction being equal to 0, positive upwards, and 0 is equal to plus RAY minus 3 kilonewton per meter multiplied by, and I should have really done this here in my image, I should indicate that this here is really 6 meters. 6 meters. And so now I can multiply my distributed force by 6 meters. And then I have to include my last force here, which is also going down, therefore it's minus 10 kilonewton. And 3 times 6 is 18 and 10 is 28, so therefore my RAY comes out to be positive 28 kilonewton. This is a result, therefore I have to double underline it and also use my answer arrow. Alright, and I can move on to my moment about A. So M about A about the z-axis is calculated by the sum of the moments about point A, and that is counterclockwise positive being equal to 0. And 0 is equal to, I start with my unknown. In this case it happens to be negative MAZ. And actually, let me rewrite this. I showed this to you before. What I often do, or what I sometimes like to do, is I have double signs. So minus for the rotational sense and then positive MAZ, because it's positive defined, right? This positive stands for, hey, this picture here is always positive, no matter in which direction it points, but this is the directional sense in the definition system here. So now I can use my other forces, which are 3 kilonewton per meter multiplied by 6 meters. And you guessed it, the right lever arm here to use would be 6/2 meters. And don't get confused here, the 6/2, you could think it's going to this side or to that side. I see that being confused sometimes in the classroom. Of course, we take the moments about this point as indicated right here, and therefore the lumped force distance is from here to here, like wherever that center is of this beam. And so the entire force will rotate this way, which is clockwise, and that makes it negative. And the same is true for our last force, which is negative 10 kilonewton multiplied by 6 meters in this case. And so I will find that my MAZ is actually negative something, right? Because if I flip this equation around, like I bring this to the other side, then I have negative here and negative there. And so the ultimate result is negative 114 kilonewton meters. But really what that tells me is, hey, Raphael, you were wrong about your initial assumption and you have to flip it around. So therefore, what did I assume? I assumed clockwise. So it must be counterclockwise. So let's fix that. So therefore, I have 114 kilonewton meter counterclockwise. And that is the real result here. So it deserves an answer error. And I want to talk about one last thing, is that you can actually almost feel this intuitively or see this here, right? So if you think of a needle pointing here into the page and you let the system rotate, right? So pretend that this all here is gone and you poke a needle into the page and you push down here, you push down here. You would intuitively know that you have to rotate back here at this location. You have to rotate this counterclockwise, while this here is turning clockwise. And so you understand almost intuitively if this is correct or not. And in this case, of course, it's correct. It turns counterclockwise upwards. And that concludes this example problem, which I believe is straightforward, and we can now make it a little bit more interesting and look at our next example. All right, so here we have our next cantilever problem, which I believe will be enough to teach us all about the support reactions in cantilever systems. So let's complete this and then move on to our next topic. What we have here is a cantilever that actually has a support on the right side, and there is a force under an angle and an evenly distributed force that is not continuous throughout the structure. So as always, let's go ahead and draw our free body diagram first and copy our dimensions over. So first I have a rigid body. It deserves the dashed line. I have my evenly distributed force that goes over 6 meters here. So I have such a system, which is 20 kilonewton per meter. And then I have two types of forces here, really, that I can break them down into a vertical and a horizontal component. So I have the first one, which is really 100 times the sine of 75, and I have 100 times cosine 75, and that one is acting to the left. Please use that correctly. So I'm going to symbolize it as such. And last but not least, I of course have my support reactions, which I assume to go up, I assume to go to the left, and I assume to turn counterclockwise, and I call this MA. about the z-axis. I call this RAX, and this here is RAY. Last but not least, let me get my dimensions so that we don't get lost when we scroll down. So I have this being 2 meters, this being 2 meters, and then this being 6 meters. And now I go ahead and solve the problem for you, or at least as much as necessary. So let's start with RAX, and I do that by the sum of the forces in the x direction being equal to 0, and that is positive to the right. 0 is equal to minus RAX, or maybe better, minus positive RAX. So minus positive RAX. And then minus, and this is really a minus, right? Minus 100 times cosine 75. And what I will find is that this equates to RAX being equal to minus 25.88 kilonewton. And that is not the result, right? Because that means that I made a misassumption here. I said negative. So therefore, it is positive to the right, which makes perfect sense if you think about it. The 100 cosine 75 pulls to the left. And to balance that, I need to use RAX, which then has to pull to the right. Otherwise, it cannot be in balance. So in other words, my RAX is equal to 25.88 kilonewton to the right. And this is really my result. So this I can now double underline and also use my answer arrow. And I can move on to my RAY, which is nothing else than the sum of the forces in the y direction being equal to 0, upwards positive, and 0 is equal to plus RAY minus 100 times sine 75 minus 20 kilonewton per meter. By the way, this is also in kilonewton. 20 kilonewton per meter times 6 meters. And notice that this completes it already because this crosses out. And now I already have the right unit. And what I will find if I solve this is that RAY is equal to positive 216.5 kilonewton. And that means that it's pointing upwards. I assumed that correctly. So I can make this my answer. And my last result now is the moment, which I calculate by the sum of the moments. So to find MA about the z-axis, I use the sum of the moments about point A in this case. And now it becomes sometimes initially confusing for students because it's the first time that they have to rotate about the other side of a cantilever beam, but you will see it's not that difficult or that different. So I start with my unknown, which turns clockwise. That makes it negative. So minus MA about the z-axis. And let's start with the 100 sine 75. So 100 times sine 75, which of course this is in kilonewton. So we need a lever arm now, right? Because our moment here has a lever arm. So what is that lever arm? That lever arm happens to be 2 meters. So that is the distance from this force to this point of reference. That's the point that I take the sum of the moments about. So let's actually highlight that. So I'm taking the sum of the moments about that point. And how does this rotate? It rotates counterclockwise. That makes this positive. Sorry, is that correct? Counterclockwise positive. Yes. Why was I confused? Because here I used a negative and therefore I was wrong there. So this is actually positive and this is also positive. So please note that I made a mistake here initially. This needs to be negative. Sorry, it needs to be positive. All right. So now I can use my other force, which is also positive. 20 kilonewton per meter multiplied by 6 meters. And now comes the trick, which is not a trick really once you understand it, but you know that the lumped force acts here, so at 3 meters and 3 meters, and we need to take the sum of the moments about this point. Therefore, we need 3 meters plus 2 meters plus 2 meters. So let's write it down as such. So multiplied by 6 over 2 plus 2 plus 2 meters. And let's understand that this is the lever arm. And this is the lumped force. So F resultant is what I usually call that. And just to be 100% sure, let's actually draw that into our diagram here on the top. So I would have a lumped force right here. And my lever arm would be this distance here. And so we're talking about 6 over 2 plus 2 plus 2 from here to here. And now all I have to do is calculate it out and find that my MA, and again, keep in mind that I made a mistake here initially. I actually assumed this to be negative, but it must be positive because it turns counterclockwise. And this force about this point also turns counterclockwise, and this lumped force about this point also turns counterclockwise. So everything turning counterclockwise cannot be true, right? Because then we would have no rotational equilibrium. Therefore, my answer must be, by all means, negative. And the numerical answer here actually happens to be 1033 kilonewton meters. So what we know is that my M is actually 1033, and that would be clockwise, right? So that is my real answer, or I could also say that it's clockwise, meaning this way, since it's a 2D description. So last thing for me to do here is to double underline it and use my answer arrow. And that completes the problem, because I now calculated all 3 support reaction at location A is what I called it. And the important thing to understand is that this support resists all 3 different types of forces and moment, or 2 forces and 1 moment. And then that I showed you that now if you have a force under an angle that is resisted here by RAX, which needs to be in balance, that's why we found the negative answer here first. Then we assumed correct RAY, we found that to be positive, and it told us that yes, we have to push up. And for our last identifier, the moment here, we found a negative answer, because you can see that if I equate this equation to MAZ, it becomes negative. And that means that we assumed incorrect, which is of course making sense, because everything turning counterclockwise cannot be true for a balanced system. So therefore we needed to rotate against it, or clockwise, with 1033 kilonewton meters. And that completes this problem, and we are now ready to tackle other distributed force types. We will do that on the next page, and I will see you there. Okay, now that we have an understanding of evenly distributed forces, it's time for us to look into non-evenly distributed forces. And the first one, the easiest one that we can deal with at this point, are triangular type forces. And let me explain to you where those occur, or when you might interact with them. So for example, when you build staggered walls, I prepared one for you right here. So let's say you have a wall that looks like this, and you need to support this type of wall on your rigid beam. So let's just use a simply supported beam, but it doesn't really matter. It could also sit on a cantilever beam. And I just pretend I want to calculate the support reaction for this system. Then I could just idealize that, and I can represent this something like this, with a triangular distributed force on it. So I would usually draw this smaller, but right now I just try to make the similarity apparent between the two systems here. And then we have force arrows that indicate a distributed force, but with a linear increment here. So it goes from 0 to whatever we usually call later on W1. And this is usually given in, let's say, kilonewton per meter as well, but don't be fooled by the per meter, because you will actually define each length arrow differently. So let's say this here, for example, would be 90, and this would be 80, and this would be 70, and this would be 60, and so on and so forth, all the way until you hit 0. But you would need to find a method to describe what force is actually acting on these support systems and how much force has to be carried by the rigid beam here on the bottom. So my first goal then is usually to define the slope of this line. And again, let's use some numbers here. So let's pretend that we have a force of, say, 90 kilonewton per meter. And let's further pretend that the entire wall has a length of, say, 3 meters, just to make our life easy here. And you remember from before that when we calculated the evenly distributed force, that it was what? Base times height, right? Base times height. And for a rectangle, so this was the area of a rectangle, right? Now, as you can see, it's not a rectangle anymore. In fact, it's half a rectangle. You can think of it also when we talk about the half, that I cut away something here. So I have half a rectangle, and of course you already see it's a triangle, and of course in your head it's already ringing that the area of a triangle is really equal to 1/2 base times height. And so you already understand how to calculate this, but again, be a little bit careful with this unit here, kilonewton per meter, because again, let's say it's 90, then it's only applicable to this arrow. Here, this arrow would be 0, and everything in between would be somewhere half that way, or a different increment of it. So for example, right at the middle, of course, it would not be 90, it would be 45 kilonewton at that per meter, if you will. So how do I calculate, in this case, what the lumped force would be? So in this case, F resultant would be equal to 1/2 base times height, so 3 meters, multiplied by 90 kilonewton per meter. All right. And so this is effectively 90 times 1.5. So what we end up with is 135 kilonewton. So this is one part of the equation. You know that the force now is 135 kilonewton. What you don't know is where it acts. Well, actually you do know, but to be clear here, I want to make sure that everybody is on the same page. And so I want to explain that anyways, even if you already know. Remember that when we had a rectangle where the force was lumped, it was right along the diagonal, right? And where the two diagonals met. Now for a triangle, I can do something very similar. I can not draw diagonals, but I can find the midpoint and connect it to the vertex on the other side. So I can do that here. So I connect that, and I can do the very same thing on the other one. And now I connect those 2 points with a straight line, and hopefully I'm doing this so correct that when I find the midpoint of the last one and connect it to the last vertex, that they actually meet in the same point. And yes, it appears I did that correct. So this is technically where the lumped force would act. And this is just the geometry of it. So this is the F resultant. But what you need to remember is really the distance from the support reactions, right? Because you need that lever arm. So what you need to remember is this distance And you can probably already tell from this picture, and you might have already discussed this in high school, that this distance here must be 1/3 of the length, and this here must be 2/3. So if, for example, this here would be equal to L, the 3 meters, so this is equal to L, and then I will find that this here would be 2/3 times L, which of course is equal to 2 meters in this case. And the other side would be equal to L over 3, which is equal to 1 meter in this case. A very simple example, but it gets the point across. So you need to remember this, that the resultant force, the lumped force, A, is calculated by 1/2 base times height, and B is located at this distance 1/3 and 2/3. And it's important to recognize that what we have here is what I call the heavy side of the triangle, and here we have the light side of the triangle. So I call this the heavy side because it's the larger portion, the higher portion here compared to this side. And so I call this the heavy side and this the light side. And so on the heavy side it's 1/3, and on the lighter side it's 2/3. And so please remember that this is how you would really calculate that. So we can now actually go ahead and calculate our support reactions. So remember that the support reactions here would be RAY, and then here we have RBY. And you can do this in different ways now. Let me just say that I use the sum of the moments about, let's say, B to find RAY by the sum of the moments about point B being equal to 0, counterclockwise positive, and 0 is equal to, I start with my unknown, minus RAY, because it's turning clockwise, minus RAY times 3 meters in this case, and then plus the F resultant, right, which was 1/2 base times height, which was 90 kilonewton per meter. And then this needs to be calculated or multiplied by the lever arm, which in this case, now be careful, we're turning about point B, so it's this one, so I need to multiply it by 1 meter. So multiply it by 1 meter. So this is the lever arm. And in this case, it's also equal to 1/3 L. And then this part here is F resultant. And so you can then calculate your total RAY. So RAY is nothing else than the force here. This was 135 if I'm not mistaken, and then multiplied by 1, so 135 divided by 3, which comes out to be plus 45 kilonewton. So the first support reaction, RAY, is 45 kilonewton. Now I want to ask you, do you already know how heavy the other support reaction must be? So we calculated this to be 45, and this one must be more, right? So it must be more than 45. In fact, you probably already understand that it has to balance the 135, because the 135 is actually pushing down on it. So we have this going down, this going up, but we need to balance the 135 not just with 45, but also with the rest. So we need another 90 here. And let's actually prove that by the sum of the moments about point A. So I'm going to do that here. The sum of the moments about point A is equal to 0, counterclockwise positive, and 0 is equal to plus RBY multiplied by 3 meters. And then F resultant rotates about point A actually clockwise, therefore that's negative, so I have to subtract the F resultant, and in this case I just write 135 kilonewton, that's the resultant, multiplied by 2 meters in this case, right? So now we can solve this equation and we will find that RBY is equal to 135 multiplied by 2 over 3, which then gives us 90 kilonewton. And you can see now the system is in balance because both support reactions plus the vertical force that comes down on it, or minus I should say the force that comes down on it, actually creates equilibrium. So this plus this is equal to that. And that is part of the concept here, and it's not important for me in this section here that you really understand how equilibrium works. In fact, you should already understand that. We talked about that. What's important to me is that you understand how the force is distributed, that we usually give the highest point, and you actually understand that there's a linear distribution from that high point to 0, and that makes it a triangle, if you will. And within that triangle, the lumped force can be calculated as base times height over 2. And it's located at 1/3 and 2/3 distance from the end of the triangle. And again, I call that the heavy side and I call that the light side. And that covers triangular distributed forces. But of course, forces can be more than triangular distributed. They can be arbitrarily distributed. And so let's talk about arbitrary forces next. And so those actually then become force functions. What does that mean? So for example, you can describe even a triangle as a function. Let's say you have a beam here and you put a force on it. And I have, let's say here, a linear function. But you can also have a constant function. That's a special case. So let's say this is constant. You can also have a parabolic function. So let's say that looks like this. So this would be parabolic. Or you could have even something that is a sine wave and repetitive function. So in that case, I need to make my beam a little bit longer here, but it can act on that as well. So each one of these is acting on the beam with different intensities, but they all share some common aspect, and you are already aware of this aspect. I just want to make sure that we formalize that properly for you. So for example, if I looked at the constant function where we started with, so let's say this part here is constant, you already know that the centroid was here, and you realize that we calculated the base times height, right? Base times height. And we located it at centroid, or the center of mass, or whatever you want to call it. I call it centroid because it's a geometric function actually, so centroid. So we have the centroid right there. Same thing here, but here we had base times height divided by 2, or 1/2 times base times height. But we also had centroid. Now, what do these things have in common is that we calculated the area here, and then here the lumped force location, right? So I call this here location. So, and that stays true for all cases. For example, if I have a parabolic function here, what I would have to do is I have to calculate the area content of this parabolic function, or everything that you see there, that would be the lumped force. And so actually let's put that here as well. So F resultant was really the area, which then really was given with these formulas. And I'm not giving you more formulas right now because my goal here is not to train you mathematically, but to understand this conceptually, that we have the parabolic function given here. We need to find how much area content we have. So you would integrate. And then, of course, you would still find that there's a centroid somewhere. You can find that as well. We will discuss that later in this class. Right now, we're just talking about that concept, but you understand that that's where the force is acting. So here again, you find A and you find the centroid. And then the very same thing is true here for our sine function. In fact, let me actually add that here, that this is sine or cosine, it doesn't really matter. The concept remains the same, that you have to calculate the area under the curve and you find the centroid under the curve, and then you can use that for your arbitrarily distributed forces. So for now, let's just memorize that we always need to identify the area under the curve to find F resultant. And in fact, you did that already, like the area under the curve, again, base times height, right? That's the area under the curve. It's not very mathematical, but it is the same concept. So we need that to find F resultant, and we need the location of the lumped force. And that, of course, is F resultant. So we need to know where F resultant is acting. So in other words, where F res is acting. And you kind of did this before as well. You already found the centroid location, right? So we will learn more about centroids later in the class, but you did this intuitively for a rectangle and maybe even for a triangle. Of course, when the shapes become a little bit more complicated, then it gets a little bit more involved. But the idea is that you need the location of that lumped force. In fact, you want to maybe write here centroid location. Of area. So it's a geometric function really in this case. But that concludes for now how we think of arbitrarily distributed forces, and we can now use, for example, triangular forces in our example problems, and we will do that on the next page. So here we have our first easy way in to non-evenly distributed forces with a triangular distributed force that sits on top of a 9-foot long beam, and it carries 60 pounds per foot at this high point and 0 pounds per foot right here, and everything else in between. And our goal now is to find the support reactions. As always, we start off with our free body diagram, and a free body diagram for a rigid body always has the dashed lines added to it. And I bring down my forces next. So let's use this triangular force with 60 pounds per foot right here. So that only applies here at this location, 60 pounds per foot. And of course, I need to include my support reactions. So I assume that RAY goes up. I assume that RAX goes to the right. And I assume MA to go clockwise. And now I'm ready to perform my calculations of this not so complicated system. So let's go ahead and actually add the distance here. So this happens to be 9 meters. And now I calculate first RAX by the sum of the forces in the x direction being equal to 0, positive to the right. 0 is equal to RAX, which happens to be a result. So I double underline it and give myself the answer arrow here. Now, RAY becomes a little bit more interesting. I do that by the sum of the forces in the y direction being equal to 0, upwards positive, and 0 is equal to plus RAY minus 60 pounds per foot multiplied by 9 feet multiplied by 1/2. Again, careful, this is it, right? Because pound per foot and foot turns out to be pounds. RAY is also in pound. So I can now calculate that this actually is 270 pound. So RAY is equal to plus 170 pounds. Plus means it's going up as before. Nothing new here. Now, last but not least, we need to include our MA, and I probably should identify this here, MA about the z-axis. So I'm going to calculate that next. MA about the z-axis is really calculated by the sum of the moments about A being equal to 0. By the way, it's also about the z-axis. And 0 is equal to, in this case, minus MA, because I assumed it to be clockwise, minus MA about the z-axis, or again, as I sometimes like to do it, minus plus, and then the 60 pounds per foot multiplied by 9 feet multiplied by 1/2. This is the lumped force, right? So this is F resultant. But now I need a lever arm, and that lever arm now actually happens to be what? Exactly, you guessed it, it happens to be 6 meters. And I will explain that to you in a second a little bit more. But first, a rotational sense. So this rotates about this point clockwise, so therefore it's also negative. So this entire thing needs to be negative. Now, where did I get the 6 meters from? I'll show it to you one more time. I have a lumped force right here. This is F resultant, pointing downwards, and I know that it's 2/3 from this point, right? So this here happens to be the distance, which is 6 meters, which is really 2/3 times 9. And that's where I got the lever arm here. This is the lever. All right, and now I can solve that. And if I solve this correctly, I will find that my MA is 1620. In my case here, it happens to be negative. So MAZ is equal to negative 1620 pound/foot. And this is not the result yet, because I know that it's 1620 pound/foot. And because it's negative, it needs to be opposite to what I said here. Don't fall into the trap to think negative means always clockwise. In fact, you see here, this is actually clockwise, right? I assumed it clockwise, which usually would be negative, as indicated here, because counterclockwise is positive defined here. But I just found that this here came out to be negative. That means I assumed incorrectly here, and therefore it turns the other way around. So it actually needs to be this way, which then would be counterclockwise. So counterclockwise, and that's technically positive, like, right? So don't confuse those two things. But this now is my result, and I now successfully solved this example problem. Let me finish it by my answer arrows here, and we get a last look on it. Please understand that this 60 pounds per foot is only applicable at this high point, and then everything down here is described by pretty much this linear function. So for example, right in the middle it would be 30 pounds, and then also understand that the F resultant acts on the light side here, so 2/3 times 9, which is 6 meters, from point A. And that, I think, is everything you need to know here, and we can move on to our next topic. Because you already developed a strong understanding of cantilever beams and you know exactly how to calculate the support reaction for the load cases that we introduced to you, let's talk about another load case that we have not formalized yet. It doesn't need much of our attention, but it needs to be addressed so that we are all on the same page. And what I want to talk to you about is called concentrated moments. You have already seen those in your homework. At least you had like 2 problems that gave you a glimpse into that. But again, we have not defined those properly. So let's talk about that real quick. So let's say you have a rigid structure that actually is under the action of rotation. What do I mean by that? So let's say I have a support reaction here and a support reaction right here. And I'm now welding something to that structure somewhere in a random place. So let's say right here, I weld something to the top and to the bottom. And that is rigidly connected now. It is one part. This is very rigid. This is all one part of the structure. And I will now apply a force to it in one direction and then a force in the other direction. So for example, let's say I apply a force here and here. And what you can see is that this type of force is actually called a force couple because they are parallel to each other and they have the same magnitude. So let's call this here F1 and then this is F1 as well. The 1 stands for the fact that they have the same magnitude. And they actually also equally distanced from the structure. So let's say here we have 0.5 meters and 0.5 meters. It doesn't really matter as long as it's equal. And what these forces do is they, of course, cause a rotation at this point, right? So we identify them with a moment. We can symbolize them as M. And so in this case, it would actually be F1 multiplied by 1 meter. And that is something I want you to think about because you may think, how is this possible? How can this force couple be replaced by this force times 1 meter? And that is because this force has half a meter and this force has half a meter of a lever arm. And you can also rotate them about this point. It doesn't really matter. Then you have this force times this entire lever arm, which then would be 1 meter. But F1 times half a meter plus F1 times half a meter is F1 times 1 meter. And so what engineers do is they replace these type of force systems by an acting moment. But you can think of these moments every time you see them as something that causes rotation. So think about you actually putting your finger on here, like out of the plane. Remember, this is in the XY plane. And now in the Z plane, you actually put your finger there. And now you rotate your finger on that structure. So you actually make it rotate this way around. So what would happen? You would probably push on this support and you would lift this support up. And that is the concept you need to understand, right? So you're rotating down on this side and you're rotating up on this side. And of course, these come in many different forms. So you can think of them not as down and up, but you have to understand when they push down and when they push up. So for example, you can also have a second moment, let's say this one here. So this here could be, let's say M2, and then that M2 is acting right here. And that does exactly the opposite. This one pushes actually down here and pulls up here. And again, if you don't see that yet, what you can do is you can take the piece of paper, put a needle here, and then rotate it in this direction. And you will see that this will go down and this will go up, right? And so therefore, this support reaction has to balance that, and this support reaction has to balance it by pulling it down. So please understand that these can cause clockwise or counterclockwise rotations, right? So for example, here for M2, we have a counterclockwise rotation, whereas for the other one, we have a clockwise rotation. And they, of course, result in different support reactions. But the support reactions are not all affected by them. In fact, let's look at the unit, right? So for example, M2 could be given with, let's say, 10 kilonewton meter. And so the kilonewton meter is a unit that only works in the moment equation, and you should not let any other equation be affected by this. So you may ask yourself, why is this? Because this obviously has an effect on the support reaction, but it only has an effect because of the rotation, the kilonewton per meter. And you can look at the blue description here and you can say, but there's forces that actually produce this, and you would be right. But notice one important thing about this force couple here. The force couple is actually in equilibrium in the x direction, right? F1 minus F1. So they are actually in equilibrium. The only thing that they do is they cause rotation. And so the moment only affects the moment equation. So concentrated moments only affect the moment equations. And by that, I'm talking about the rotational equilibrium. Which we usually describe as the sum of the moments about any point P being equal to 0. That is what we need to affect it. They do not impact force equilibrium. All right, and that is all we actually need to know or learn about concentrated moments. The rest we learn through application when we actually look at the following example. So what we need to know about concentrated moments conceptually is given here, and the rest we will now study through application. Let's go ahead and solve the problem. So here we can see a cantilever beam that's supported on the left side, has an even distributed force acting on it, and two concentrated moments. One with 100 kilonewton per meter, 100 kilonewton meter, and another one with 100 kilonewton meters. And now we are asked to find all support reaction for that cantilever beam. As always, let's get started with our free body diagram. So I am copying this system down, and I will use all my forces. For example, here the 100 kilonewton meter, and then here my 150 kilonewton meter, and of course also my evenly distributed force, which is acting over 4 meters. So let's now go ahead and add the support reaction RAY, RAX, and MA about the z-axis. All right, and that's all we need to get started. So let's go ahead and run our calculations. So to find RAX, all I have to do is take the sum of the forces in the x direction being equal to 0, and therefore 0 is equal to RAX. And that is a result once again. To find RAY, what I have to do is take the sum of the forces in the y direction and set it equal to 0, upwards positive, and 0 is equal to plus RAY minus, and shame on me, I didn't calculate how much this is, so this is 20 kilonewton per meter. So 20 kilonewton per meter is now going downwards, so minus 20 kilonewton per meter multiplied by 4 meters. It's acting over a distance of 4 meters, and therefore I know that my RAY, first of all, is positive, and I indicate that it's positive, and then 20 times 4 is 80, plus 80 kilonewton. This means it's going up. All right. Now, last but not least, we have to move on to the moment equation. But before we move on to the moment equation, note that in this equation, these two concentrated moments had no impact. They were not included in my equation, and they are not part of anything here because, as I mentioned to you before, there are no forces that are not in balance, and therefore they don't have to be added here. It would be incorrect to add them. Now for the moment about A, we would take the sum of the moment about A and set that equal to 0, counterclockwise positive. And I assumed that to be clockwise, so therefore 0 is equal to minus MAZ. And let's start with the 20 kilonewton. That would rotate, of kilonewton meter that is, that would rotate clockwise, so 20 kilonewton per meter multiplied by 4 meter. Notice that it's not a moment yet, it's only a force because those two cancel out. So I have to multiply that by the lever arm, which happens to be 4/2 meters. And again, that rotates clockwise, therefore this is negative as well. And now I have to add my two moments. So I have the 100 kilonewton meter, and that one rotates counterclockwise, therefore it's positive, and the other one rotates clockwise, so therefore it's negative, so minus 150 kilonewton meter. And yes, it is that simple, but don't worry if you get confused why we're even learning this if it's so simple. You will see later on when we deal with internal forces that they will have to be dealt with in a very special way. This is just to get you used to these concentrated moments and what effect they have on the two different types of equation, force equilibrium and moment equilibrium. So you'll see that here we just added them depending on their rotational sense. Last thing for us to do is to find the answer to MAZ, which in this case comes out to be negative 210 kilonewton meter. So in other words, my MA about Z is actually 210 kilonewton meter, and that rotates counterclockwise, right? So counterclockwise or this way around. And that is my true answer here. So this needs to be double underlined and also needs an answer arrow, as do all the other ones for this example. So let's finish that. And this is now done, and we completed our first cantilever problem with concentrated moments, and we know now how they affect our equilibrium equations for forces and our equilibrium equations for moments, or I should better say how they do not affect our force equilibrium equations but our moment equilibrium equations. So that completes our lecture, and we can now move on to the homework and to the conclusion of our learning experience. So let's conclude the lecture and let's talk about our takeaways, or better said, you go ahead and define what are your takeaways and what you have learned, just as much as what's still not clear to you and where you need more clarification. And once you're done with that, let's move on to the final checkpoints and let's talk about our goals for this lecture and what we had in mind to teach you here specifically. So first of all, it should help you to understand what self-weight of a structure really is and how you can represent that by evenly distributed forces. So please make sure that that is clearly understood. Then you learned with the evenly distributed forces that you can actually lump a force into a single concentrated force, at least conceptually, so that you can apply this force at the center of the evenly distributed force for your calculations. So that should also be clear, and I think that was taught throughout this lecture. Then you definitely learned about the resistance that a fixed support really provides. So let's make sure that we understand the fixed support. And last lecture we called that restricted degrees of freedom. And we today use that to clarify that all three types of equilibrium are balanced at that one location, at the fixed support. That is something we definitely took away from this lecture. And that also helped us to study and learn how to solve support reactions, all three support reactions for cantilever beams. That was the only thing we discussed in this lecture, cantilever beams. And we did that for the distributed forces and the concentrated forces. So we can definitely check that off. But we also learned that the system can be much more complex if you have non-evenly distributed forces. So we are aware that this, of course, is all an idealization and that in real life it can be more complex. In fact, when it becomes more complex, you may end up with non-evenly distributed forces, but you learn that they can also be lumped up into a single concentrated force simply by finding the area under the curve and then find the location, so you understand where this concentrated force must be located. At least conceptually, we talked about that. And last but not least, we talked about the concentrated moments and how they affect the equilibrium equations and what they do to a structure. So when you solve for support reactions, you know now how to deal specifically with concentrated moments. So we can check that off. And I believe those are enough and good goals for one lecture so that we can now move on and talk about the homework assignments. For the upcoming homework, it is probably not a surprise to you that we're dealing with cantilever beams and cantilever beams only to apply our newly gained knowledge. But let's take a look at the individual problems and what you have to do here. So we're not trying to insult your intelligence here with the first problem. It probably looks too easy to you, but we want you to have an easy way in and give everybody the same chance to develop their knowledge. So very simple problem, support at A, a fixed support at A, and then only one concentrated force at the end of the beam. I don't think it gets any easier in this class. But again, we're not trying to insult your intelligence. We're just giving everybody a chance to perform from the ground up. All right, for the next problem, it becomes a little bit more interesting. Support as well on the left side, and we have now forces in two dimensions, in the X and in the Y direction. There's also a force here at the end of the cantilever beam. So this speaks for itself, I believe. Everything is given here, the angles and the forces and the distances. So I'm sure you can solve that as well. Then we have probably the easiest distributed force problem here waiting for you, where it's just a single distributed force on the entire length of this cantilever beam, with the support in this case on the right side. Let's move on to the next problem where it really becomes interesting. And here you have to deal with all the different load cases, or some of the different load cases, distributed force, concentrated force, and a moment, all acting on a cantilever. And I believe I don't have to say much about this problem. I think all the information is contained within this lecture. Then we have a triangular distributed force here for the specific case where the heavy side is actually close to the support. And that also doesn't require much information because it was all explained throughout the lecture. Last but not least, we have a structure where the heavy side of the triangle is far away from the support. So here you have a triangle that doesn't act over the entire length. But I think how to solve this does not require a lot of explanation right now. All that information is contained within the lecture. I wish you good luck with that. In fact, I wish you good luck with the entire homework. And I will see you in the next lecture. Stay safe.